Okay. So who in here has heard of the term solutions? Anyone? Okay, a number of you. Okay, anyone want to venture? What is a solution? Frequently they'll say, my coffee in the morning, I have to put sugar in it. I stir it around and the sugar goes away, quote unquote. Is that an example of a solution? Yeah. Now, the uncommon definition of a solution does more than water and something dissolving in it. It's much more than that. For example, a gold ring is a mixture of copper and gold, not just gold. So a solution is defined as two or more chemicals in a homogeneous environment. That means you can't tell the difference between the copper and the gold, or between the sugar and the water, or as an example in here, the air we breathe is a solution. It's got two or more chemicals in a homogeneous environment. You can't tell the nitrogen from the oxygen. So it's a solution too. We're going to focus on water-based solutions for Unit 3. Okay, water-based solutions. Now, all solutions have two parts. They've got a solvent and a solute. Now, the minimum is two parts for solution. The part that is most is the solvent. The parts, possibly more than one part, okay, is what's dissolved in the solvent. Okay, so you can only have one solvent, like in the air example I gave you. That's going to be nitrogen, is going to be the solvent. The solutes are going to be oxygen, carbon dioxide, hopefully no carbon monoxide. Those would be solutes because they're less than the solvent. And you can have more than one solute, but one solvent. Now, there's a lot of words there that sound the same. So solvent, the most. Solutes are less than that, and you can have more than one. Okay. Let's look at a crystal of sodium chloride and we throw it in water. What happens to the sodium chloride? What happens to the table salt? Does it stay whole? I'm not talking about adding 2 handfuls in a little bitty glass. I'm talking about a tablespoon of salt in a good sized glass. What happens to the salt? It what? It disappears, right? Okay, so let's look at that process of the disappearing solute. So in the case of the example I just gave you, salt and water, the water is the solvent, the salt is the solute. Okay, so water, as you remember, is very polar. It's got 2 hydrogen bonds going in it. Hydrogen bonding is the strongest intermolecular force, and it's got 2 in it. And secondly, they're not pointed in the same direction, the dipoles. So it's even stronger. And our whole world has got a ton of water in it. A ton. And they're believed to be an ocean underneath the crust of the earth also, to add to that huge amount of water. So sodium chloride is an ionic solid. That means it's made up of ions, cations and anions, positive and negative ions. So what's going to happen is the water is in motion. The salt crystals are in motion, unless we're at absolute zero. Otherwise, everything is moving. So statistically, the odds of a water molecule hitting the surface of that crystal is high. It's going to bump up against the crystal. What happens then is the sodium cation and the negative part of the water is going to be attracted. And what's going to happen, that water is going to pull that sodium ion out. Likewise, with the chlorine ion is going to be pulled out by the hydrogens because they're partially positive. So this water is going to kind of massage this salt crystal and start pulling it apart. Now, the main thing, this is a surface phenomenon. The more the surface, the higher the rate of dissolving. So which dissolves faster? Hot coffee with your sugar in it or cold coffee? Hot coffee. That's because hot coffee has more movement of the water in there. Hence, statistically, there's a higher chance of that water hitting the surface of the salt. So if it happens faster, the crystal dissolves faster. Slow down, dissolves slower, until finally we are at absolute zero and no movement is. Okay, so one of the variables is temperature for the salt dissolving. Higher the temperature, the more movement. And how do we measure movement? Remember? Yeah. It's energy. Remember what kind of energy? Energy. What is the energy of movement? Is it potential energy? Or that's right, kinetic energy. Perfect. Okay, so how do we measure kinetic energy? How do we know the water's hotter? Temperature. Temperature. So temperature is a measurement of kinetic energy of the solution. So we're going to use temperature as the metric. So when the temperature goes up, movement goes up, dissolving increases. So we can say that mathematically, like this here, number one, temperature is directly proportional to the speed of dissolving. Okay, that little infinity sign on its side cut is directly proportional. Okay, it's important to not connect the right side there. Okay, so let's go back to your coffee again. If we just throw the sugar into the coffee and do nothing, will it dissolve? Yeah, eventually it'll dissolve. How can we make it dissolve faster? Stir it, right? Because by stirring it, you're increasing the rate of the molecules moving. So increase the odds of that water hitting the surface of that crystal. So physical agitation is directly proportional to dissolving. Okay, so if we've got a rock candy chunk of sugar, size of a marble, and we've got powdered sugar, which is going to dissolve faster in the coffee, the powdered sugar or the big chunk of rock candy? Powdered sugar. Why do you think that is? You're right, but why do you think that is? Am I putting you on the spot? Yes. For that crystal to dissolve, what must happen? What must the water do? Or hit it, right? So you can attract it out. If you have a sodium inside the middle of a crystal, will the water affect it? No, it won't. It has to be at the surface only. So the powdered sugar has more surface area than the chunk of the rock candy. Hence it dissolves faster. So these are the three variables that affect dissolving. Temperature and physical agitation are connected directly because they both involve increasing the motion of the solvent and then increasing the surface area of the solute. It also affects. So all three of those are directly related to the speed of dissolving. Okay. Let's look at two more solutions. Let's look at one solution with sodium chloride and water, and the other one with sand and water. Okay, in the first one on the left, what's the solvent? Water. What's the solute? You're doing great. What's left over? The salt, right? That's the solute. Okay, solute, solvent. Solvent's the most, solute's the least. Oh, multiple solutes. One solvent, no exceptions, one solvent. We can make an argument that once it leaves the crystal, it's no longer one solute, it can be two. But okay, on the right, sand and water. What's the solvent? The water. What's a solute? Sand, yeah. What's the difference between these two? Sand is silicon oxide, pretty polar. They're both, so the solutes are both polar. The water's polar in both of them. What's the difference between the two of them? Can we stir the one with the sand in it and get it to dissolve? No. Sand is the same thing as glass. We have an aquarium made up of glass. It wouldn't last very long if we just stirred it a little bit and it dissolved. So sand just stays sand. So there are two forces working when we have a solution. We have a solvating force, which is the force of the solvent pulling the crystal apart. Then we have a crystal lattice force that keeps the crystal together. And it's a balance act, which is stronger. If the crystal lattice force is stronger, like here, it stays together. If the solvating force is stronger, it dissolves. Now, those two forces, one is temperature dependent, the other is not. Crystal lattice force is not temperature dependent within reason. Solvating force is temperature dependent. So if the crystal lattice force is stronger than solvating force, increase the temperature of the water. So you're increasing the solvating force by increasing the temperature. Okay, on your tests, you will have guaranteed a question like this. and we ask you to describe with a diagram how a crystal dissolves. Okay? Every test I've given in the last 20 years teaching this prep-like class, I've given that question out. Okay. Now, I want to show you something here. I teach biochemistry at Sac City. And when you're in an organic / biochemistry class, there's a lot of structures. One of them is glucose. And my students can do glucose in their sleep, along with a whole bunch of other stuff. Notice something about glucose. What stands out in that molecule? Yeah, not only hydrogen, but oxygen, hydrogen, hydroxyl group, OHs. OHs, hydrogen bonding. So sugar is very, very polar because of all the whole hydroxyl groups. And guess why sugar easily dissolves in water? So it is not ionized like sodium chloride is. Excuse me, it just has a whole bunch of polar groups on it, which makes it easily dissolve. There's a saying, like dissolves like. Polar things dissolve polar things really easily. Unpolar things dissolve unpolar things really easily, like fats and oils. Those are very nonpolar. So you want a nonpolar solvent dissolve. Okay, so that is the qualitative part of solutions. I wanted to give you an idea of what is a solution, what are the parameters that make things dissolve or stay not dissolved. Okay, and at this time, we are going to have a student survey. Now, after the survey is over, we're going to start on the quantitative aspect of solutions. And guess what we're going to talk about? We talk about the quantitative aspect of solutions. And unit 2, what is everything related to? What unit? Moles, right. So guess what? Solutions are going to involve moles per liter. So, all right. So I'm going to pause let's see here. Okay. So as you know, in solutions, we've got solute and solvent. Now, quantitatively, as you know, involves numbers. So quantitatively, we're looking at two calculations. One is a very popular one. The other one is a little more lesser used than the top one. And here we're only using the top one. It's molarity and molality. They're very close sounding, but they're different. One is moles of solute per liter of solution, and the solution includes solvent plus solute. Molality is moles solute again, and kilograms of solvent. Now, sometimes these calculations work out to be very similar, and other times very different. Okay, usually thermodynamically, we talk about using molality. Things like when you add solute to a solution, the boiling point, melting point changes, that kind of stuff. Then you use molality. But in here, we're going to be using molarity, just moles per liter. Moles of solute per liter. Okay. And sig figs come into play and all that stuff, just like in unit 2 and unit 1, actually. Now we're using liters, not milliliters. If it's milliliters, you convert to liters. And we're using moles and grams. Okay. All right. So what is the molarity of the following solution? 34 grams of sodium chloride and 345 liters of water. Okay. So we're given grams, not moles. So we need the molar mass of sodium chloride from the periodic table. That's going to be 58.44 grams per mole. So what's given? Given is 34 grams. Okay, now we need to convert to moles. We're going to have moles over grams. So the grams cancel, collect with moles. Now we're going to have, this will give us how many moles of sodium chloride are in that solution. Now, this is going to be the easiest conceptual way to do this problem is in 2 steps. First, get it to moles. And what's the volume after that? Okay, so let's do this. First, we get it to moles, 34. And all that's going to be over 345 liters. Now, there's 2 ways, computationally, there's 2 ways to work this problem. We can do it in 2 steps. First, we can calculate moles, and then we put it over the 345 liters. Or in your calculator, you can do this all together. And the advantage of doing it all together is your calculator will take care of the sig figs for you. If you do it in 2 steps, I want you to do it by not rounding. You round in the end. Otherwise, you'll get rounding errors. Okay, so I'm going to end up doing this calculation. We're going to end up with .1713 sig figs moles per liter. Now, there's an abbreviation for moles per liter. And that's uppercase M. And I usually italicize it, boldface it, just so that you know it's not meters, it's molarity. Okay. Now this is simpler than what you've been doing in unit 2. We had this pretty long problem in unit 2. And this is pretty straightforward. And of course, we're going to be adding to this as we go along. Okay, so any questions about this process? Conceptually, get it to moles, like everything we've done so far. If in doubt, convert to moles. If in doubt, convert to moles. Bless you. Okay, so let's look at another problem. How many grams of sodium chloride are there in 3.45 molarity solution with a volume of 5.67 liters? Okay, so I want to go back to simple algebra. This is our all unit cancellation. What is the answer to that algebra problem? You all know how to do this. C, right. We have unit cancellation, just like whenever we have the given, we always want to cancel the given. First step, cancel the given units. Okay, so here, we have so if we multiply the molarity, this is the molarity right here, by the volume, what do we get? Moles, right? So look at this problem. We've got molarity, we've got basically concentration times volume gives us moles. And then once we have moles, we can go to grams. So we're going to go. And I'm going to keep it in moles per liter rather than the big M. So liters cancel, gives us moles. Once we have moles, we can get grams from the molar mass of sodium chloride. So now we multiply by the molar mass of sodium chloride. Remember, do not round until the very end. So that's how many grams, a little over 1,000 grams in that solution. Okay, so we're going in two different ways attacking this concentration problem. Could have also done this in one calculation on your calculator by taking this guy by doing a one step on your calculator. Here we have moles cancel, liters cancel, leaves us with grams. Just if you do it in two steps, don't round on the first step. Keep it in your calculator memory. All right, now those are fundamentals of solution chemistry, calculation-wise, okay? Moles per liter. Everything's based on that. Now, remember the liters we had in Unit 2? What kind of liters were those? Gas liters. Gas liters and liquid liters, totally different animals. Totally different. Remember we used the ideal gas law at standard temperature and pressure of 22.4 liters per mole of any gas? That doesn't hold at all for liquids, because liquids are much more compact, much more condensed than gases. Gases have lots of room in between each molecule or atom. So they're compressible and all gases act the same, except under extreme conditions. Liquids are not that way at all because they're very condensed compared to gases. So we have liters and we have liters. So don't be using 22.4 liters per mole with liquids, okay? All right. Now, this is sort of a trick question, and it will be on the test as well. Okay, if you work in the stockroom, one of the main duties of a stockroom person is making up solutions for all the labs. So they'd have to do this every single day they're in lab. They're working in the stockroom. Make up. So basically we have so for this problem here, we need 1.15 times 10 cubed grams of sodium chloride and 5.67 liters of solvent or water. So how do we make it? Directions, how to make it. Step number one is to take and put your 1.15 grams of salt in something called, a fancy name for it, it's called a volumetric flask. Okay, I'm using a beaker here, but its official name is volumetric flask. Those are very accurate ways of determining volume for a water solution. Okay, so we put all the sodium chloride in the bottom there and we fill it with water. How much water do we put in? How much? Why don't we put in 5.71 liters? I mean, doesn't that save us a step? Okay, off topic here. Who's taking a bath? Okay, usually the women all raise their hand. None of the guys. Okay, what happens when you sit in a tub of water? What does the water do? Does it go down? It goes up. Why do you think it goes up? Because your body is in the water now, taking up room, and the water can't take up the same room as your body. So where does it go? It goes up. So if we have 1.15 times 10 cubed grams, and we put in exactly 5.67 liters of water, are we going to end up with 5.67 liters of water all said and done? For the amount of volume of solution? It's like when you sat in the tub, the water went up. When we put that salt in the water, guess what the water did? Up. So we can't put all the salt in, or excuse me, we can't put all the water in right away. We've got to get it dissolved first. Once it's dissolved, then we bring it up to the final volume. Because we want remember the volume is solute plus solvent for the total volume, not just the water. It includes the solute. So these are the directions. Now, it says add 1,015 grams of sodium chloride to 4 liters of water. and mix till totally dissolved. Doesn't matter if it's 3 liters, 4 liters, or 5 liters, as long as it's less than the final volume. Now, there's a little caveat there, is if you use too little of starting liquid, you're gonna end up super saturating it. You have to use enough water to totally dissolve it. Totally dissolve. But less than the final volume. Okay, once it's totally dissolved, then bring it up to final volume of 5.71 liters. Okay, that will also be on the test. I will say, give me directions how to make this solution. And these are your directions. It doesn't matter if it's whatever the initial volume is, as long as it's less than the final volume. Okay. Let's do another problem here. 345 grams of sodium hydroxide is added to 2.34 liters of water. What's the concentration? Now, let me give you a very practical problem. You all know that safety is extremely important in lab. One of the reasons why I sign off on your cleanup is to make sure you have no solutions on the countertop. Because what happens when a solution the next morning, what happens to that solution? What does it do? Dries up. Yeah, you end up with a spot, right? What if that was a weak acid? It's like a very, very weak solution of hydrochloric acid on the counter. And you walk in the next morning, and instead of 4 liters of hydrochloric acid, it's now down to 1 liter of hydrochloric acid. What does the hydrochloric acid do as the water evaporates from it? It gets more concentrated. So this very weak solution of hydrochloric acid is very, very harmless when we made it up, because we purposely made it real weak. But if we don't clean it up, the next morning what happens, it concentrates. So it becomes stronger and stronger and stronger because the water is evaporating. That's why it's extremely important to clean up everything. Because you end up with these weird situations where at one time it's safe, 8 hours later it's not safe anymore. And it's because of these type of calculations. So let's do one. Let's say okay, so we let's see. Let's make it bigger. Okay, what's the concentration of 0.15 molar hydrochloric acid, HCl, after evaporating from 4 liters down to 2 liters? So gut level feeling says that it's got to go up. So when we're all done, we need to look at the answer. And does that answer make sense? Did the concentration in fact go up after we've done the calculation? If it doesn't, something's wrong with your setup. Okay, so what are the units of concentration? 2 units. Moles per liter, right? So first thing is, let's calculate the moles, what we're starting with. So we have volume and we have concentrations. So let's look at initial moles of HCl. So we have okay, so that's going to be 0.6 moles of HCl. Now, what's our final volume? Final volume now is 2 liters, right? So now our concentration is 0.3. So the concentration went from 0.15 moles per liter to 0.3. So notice it got more concentrated. Now, if we let it evaporate down to like 0.25 milliliters, it'll even be more concentrated. So the message here is when water evaporates out of a solution, it gets more concentrated. If the solution happens to be an acid or a base, danger zone, because it's going to become more and more concentrated. Hence the cleanup part of doing labs. Now, you guys aren't going to have very strong acids and bases. What you will have one, the very last lab is a titration lab using sodium hydroxide lye. Strong base. We have to be careful with that. I'm going to start off fairly dilute, but we leave it out, it could get really strong. Okay, so what I want to do next week, let me give you some examples of some solution problems. I've got one beaker that's got 2 liters of this is what I'm going to start off with next week. 2 beakers, A and B. We've got both aqueous sodium chloride. We've got 4 grams in one 5.12 liters. The other one's got 8 grams and a little over 2 liters. We dump them together. What's the final concentration? We dump them together. See here. So So that's what the problem is. We're gonna start off with writing. Okay? All right, any questions about this solution stuff? Okay, so let's stop here.